Good afternoon, everyone. I'll be presenting DCPerf. I'll talk about the motivation behind building this benchmark suite as opposed to leveraging the existing benchmark suites that already exist. I'll talk about the design and validation process. I'll talk about the design and validation process behind the benchmark suite, and finally discuss a few use cases that we have made use of internally at Meta for these benchmarks. I would like to call out that we have been making use of these benchmarks to make design and procurement decisions for millions of servers in the fleet. And essentially, like, the reason for open sourcing it is so that, like, we can foster community-based innovation in this space and have a more robust benchmark suite that everybody can make use of. So just a little bit of background about the fleet and the motivation behind this. So we have 30+ regions with millions of servers in our fleet. We have multiple applications that serve billions of users. In the backend, the infrastructure that we have is actually composed of hundreds of large services and thousands of medium and small services that constitute the fleet. The overall fleet actually is composed of compute, storage, and AI servers, and the compute servers themselves have thousands of different kinds of services that run on them. Each service follows a service-oriented architecture, which allows us to better scale and maintain these applications in the overall fleet. As you can imagine, at this scale, the compute roadmap decisions and any kind of design choice that we make impacts a pretty large infrastructure spend and essentially impacts billions of users. And so, we need to make these decisions in a very data-driven fashion with good quality data. While good quality data is important, one of the fundamental challenges with any kind of production-based testing is it requires a rack-scale infrastructure, a very robust software stack, so that we are able to run live traffic, and then proprietary tools and telemetry so that we can monitor the hardware and software and make sure we are not causing site events, right? Which is fundamentally opposed to what you can actually enable in hardware, especially in the early stages of development life cycles, right? So we generally have access to simulation, emulation, or a very few engineering samples, and can't really run production code on these machines. In addition, essentially, any kind of decision that we need to make, we need to leverage these small set of machines to do any kind of A/B testing to make the decisions. So naturally, highly representative benchmarks are a very good and valuable tool that can bridge this gap and allow us to do informed decision making through the overall design process. We have used standardized benchmarks extensively. I'll talk about spec here, but the takeaways apply to other benchmark suites that we have played around with. One of the fundamental concerns with these benchmarks is the accuracy and their ability to predict performance of these performance of production applications that we have, right? So the plot here shows gen-over-gen performance of or performance prediction error when we use spec 2006 or spec 2007 or 2017 relative to our production applications. As you can see, there is a pretty wide gap in spec's ability to predict production performance. So any decision we make using spec is naturally going to be pretty error prone. In addition to the accuracy problem, there are other fundamental limitations with these standardized benchmarks. They are not really amenable to hardware-software co-design. They're not really very useful for system design aspects of things. They're still reasonably well for core microarchitecture level stuff. And they don't really reflect the system architecture level bottlenecks of the hyperscaler or data center environments completely. Finally, they don't evolve as rapidly over time. The hardware systems have been evolving pretty rapidly, so as the software stacks, and the standardized benchmarks have not been keeping up to the pace we would like them to. Right? So DCPerf is essentially designed to address some of these fundamental problems. At a very high level, DCPerf is a combination of few representative benchmarks that represent some of the major workloads that we run in Meta's data centers. We have leveraged open source as much as possible for ease of use. Each benchmark is designed to be similar to a service that we would deploy in a fleet. It's modular, parameterized, and scalable so that it can basically be configured to run on different kinds of hardware. Each application or benchmark itself is intended to run on high core count machines, the latest and greatest operating systems, and Linux kernel stacks. The goal from these benchmark suite is, in addition to hardware performance evaluation, we essentially want to use these for any kind of early stage software optimizations and hardware pathfinding. Hardware software co-design, where we have to do essentially library development to leverage new hardware features. And finally, this, like all of this is, like most of our development is in open source so that we can collaborate with industry and academic partners as part of this process. Let's quickly look through the design process of the benchmarks themselves. The first phase of the process essentially involves doing a deep dive into the production workload that we are trying to benchmark. We would start with the code profiling part of it, where we would deep dive into the key kernels, common libraries, data center tags, pieces of code that execute as part of the application, and look at the throughput and SLO matrix that the application would care about. Subsequently, we would dive into like more core and system microarchitecture aspects to understand how the application is stressing the system. We look at board and system level telemetries to understand power profiles, understand frequency modulations, DVFS behavior, things like that to understand how the application is interacting with the power management system of the box. And finally, we will look at CPU utilization, threading models, thread over subscription ratios, context switches, and like a broad set of memory, network, and IO parameters to understand like what are the other system level bottlenecks in addition to like microarchitecture that could impact application performance. Once we have this broad deep dive of the application, we'll start the benchmark development, fundamentally starting with the like picking an open source framework which serves as our skeleton. We will add functionality to mimic what the production application would do, and then fine-tune that functionality such that the benchmark itself is representative of the production application that it's trying to mimic. Finally, once we are confident that this benchmark itself can serve as a reasonable proxy, that's when we would add it to the benchmark suite itself. In terms of the components of the DCPerf repository, there are application benchmarks. We currently have 6 of them representing a few broad categories of workloads that we run on our general purpose compute servers. But in addition to that, we have a set of representative micro benchmarks for some of the key data center tags libraries. A couple of examples are Thrift, which is our global RPC framework that we use for service level communication, and ZSTD, which is our de facto data compression algorithm that pretty much every service uses. DCPerf also has hooks, which allow us to do detailed deep dives on hardware and software level telemetry, so that we are able to run these while running the benchmarks and enable us to do like deep dives on performance. And finally, DCPerf provides an automation framework to install, run, and report the scores so that we are able to compare, or easily compare the performance across different machines. The benchmark suite itself is ported for both x86 and ARM so that we can do cross-architecture comparisons, and it supports latest operating system and Linux kernels. Let's chat a little bit about how we validated DCPerf. I'll take a couple of examples, and there are many more in the paper. So in terms of the ability of the workload to predict performance, essentially this is the same plot that we looked at a couple of slides ago, but now we add DCPerf to the mix. As you can see, DCPerf does a much better job at predicting the performance with a 3.3% error rate over 4 generations of hardware. This is much better than like what we had initially imagined, and like we have validated this across a much wider set of hardware generations and configurations, and the error rates stand pretty constant. The other way we validated DCPerf is we looked at, as an example, we looked at top-down analysis of the production applications. Pairwise did a comparison of the benchmark that it's supposed to represent, which are the bars on the left-hand side. And then on the right-hand side, we have the spec 2017 top-down breakdown for reference. As you can see, DCPerf does a much better job at mimicking the key bottlenecks from a microarchitecture stalled pipeline perspective relative to something like spec. One of the common things like we and other hyperscalers have published in the past is like front-end bottlenecks being a key issue. And as you can see here, like the lower bars on the left-hand side kind of show that DCPerf does a much better job at capturing these front-end stalls as opposed to something like spec. There are, as I mentioned, like there are more degrees of validation that we have done to make sure that the benchmarks themselves are representative. With that, let's jump into a few case studies of how we've made use of these benchmark suites, right? So the first one is like when we were making the decision to deploy the first generation of ARM server, we had to pick between 2 options. We had very early silicon, couple of systems and labs, and so we didn't really have the ability to run production services, and so we fell back to DCPerf to make those decisions. What we did was essentially pick the baseline skew and the 2 ARM options that we wanted to evaluate. And then essentially this plot shows the performance per watt comparison of each of the individual benchmark and then overall aggregate score of DCPerf. As you can see, ARM option A does a pretty good job relative to the baseline, and ARM option B has a meaningfully lower performance. Further deep dive into why there was such a significant gap, we observed that like the front end or web serving workloads were the ones that suffered significantly on ARM option B. And kind of like this was attributed to the cache architecture choices of the benchmarks, of the architecture that the ARM B option chose. If we were to use spec and trait to kind of make this decision, we would have gotten a very different picture, right? So even though ARM option B had a significantly lower performance, it actually did, on DCPerf, like it actually did very well on spec and trait, right? So if we were to just make use of spec and trait, we would not have been able to make this decision as easily, or like we would have taken much more time to get to the same point. The other case study is around guiding microarchitecture level optimizations. So in this particular case, we worked with a CPU vendor to optimize for Meta's web workload performance. We used MediaWiki workload, which is part of DCPerf as a proxy, to essentially iterate with the vendor. What we did was over time, essentially like over the course of like a quarter, we essentially asked the vendor to help us with microarchitecture level tunings. And see like what basically could help with the production workload performance. As part of this joint exercise, we were able to identify things like TLB level LRU policy improvements, DVFS algorithm improvements, and optimizing for a different total thermal design power operating point, and get a 48% per watt win on this production workload at the end of 10 weeks. Just to remind you, like this is a pretty large scale we are talking about, and so 48% is a really large number to achieve in such a short period of time. We did backtrack and did the same exercise whether we would have been able to do something like this with spec, and not really. Like the answer was that like it doesn't really correlate with the improvements that we saw in these particular cases. The final example is where we used a particular benchmark in DCPerf to do Linux kernel optimizations. Essentially, we were trying to launch a new core architecture which had much higher core count on the, or rather like a SoC which had much higher core counts than what we were used to in the fleet. We ran on Linux 6.4, which was the kernel we typically would run in the fleet at that point in time, and we ran into a bunch of like scheduler-related issues on this particular benchmark. What we observed that the Linux kernel itself on 6.4 version was taking a significant amount of time on the kernel scheduling functions. We used the benchmarks to again like iterate and improve the kernel, made patches, landed them in kernel 6.9, and then essentially we were able to get the benchmark performance to where we would have like essentially to scale with the core count that we added on the machine. Overall, in this particular case, DCPerf was able to help us quickly iterate and get to a right kernel optimization point. Again, in this particular case, interestingly, none of the micro benchmarks or even like dedicated kernel scheduling micro benchmarks were able to identify this issue. Primarily, and the issue was primarily around like interaction of user space and kernel space code. DCPerf by any means is not complete, like it keeps evolving. We have been adding new workloads and new benchmarks for some of the emerging applications in the fleet. We are developing a DCPerf mini version. Think of it as like a short version that is more amenable to simulation and emulation environments. And then finally, we are refreshing it to keep up with the emerging hardware and software trends, things like tiered memory solutions or hardware acceleration and offload opportunities, with the goal to see that like the benchmarks themselves can be used as a vehicle for hardware-software co-design for some of these features. In conclusion, DCPerf is a representative benchmark suite. We have validated and battle-tested it for the last few years, and actually used it for decision-making for millions of servers in the fleet. We have made it open source to foster community innovation, and then of course, like we welcome contributions from other hyperscalers and the broader community so that we can all benefit from it. With that, I'll conclude, and I'm happy to take questions.
Yeah, thank you. Please come up for questions.